How about now? Can we get a thumbs up from the chat that the sound is working? Yeah, we got a thumbs up. Okay, so I can start again.
So sorry about that, and I'll reintroduce the bio of today's speaker. So let me find the bio. Wait a second. Sorry for a delay. And today's speaker, Dr. Ruslan Shaydulin, is an applied research lead at the Global Technology Applied Research Center at JPMorgan Chase. His research centers on applying quantum algorithms to classical problems with a focus on optimization and machine learning. Prior to joining JPMorgan Chase, he was a Maria Goldberg Meyer Fellow at Argonne National Lab. Let's welcome today's speaker, Dr. Shaydulin, to give today's talk.
Thank you, Jing, for the introduction. Hopefully this time the technology doesn't let us down. I'm going to talk about our work with on parameter setting for QAOA. This work has been co-led by Dylan, who's a researcher here at JPMC, and Shri, who was an intern with us last summer and has now joined us full-time. We have an amazing internship program. Jiding who's the host of the seminar, is the intern with us this year. And the applications for summer 2024 are going to open in September. So please consider us if you're looking to work on quantum algorithms in a more industrial setting, as well as if you love the idea of living in New York for a little bit. Okay. The setting, which many of you may be familiar with, is the quantum approximate optimization algorithm, or QAOA. QAOA solves optimization problems in the following way. We start in some initial state, which is problem dependent, and we apply pairs of alternating operators, where the green one is a diagonal operator encoding your objective function to be minimized, and blue operator is the mixing operator, which does not compute with phase and which creates non-trivial dynamics in the desired subspace. The goal is to prepare a quantum state such that upon measuring it, we get a good solution with high probability, which is captured by this figure of merit which we have on the bottom. Now, the alternation operators in this circuit have free parameters in them. And it is commonly pointed out that these free parameters in general are difficult to set. So there is a number of theoretical results showing, for example, that in certain settings, even for easy optimization problems, the problem of finding these parameters is NP hard. What I'm going to discuss today is that in a broad range of cases, this parameter setting problem is in fact easy. We can either obtain analytical parameters in closed form, or we can show that the optimization is simple. Now, why would we want to study QAOA? First, it's one of the few quantum algorithms for solving optimization problems, so that's already something. But also, there's a number of preliminary evidence showing that it performs rather well on certain problems. So, for example, for SK, it outperforms semi-definite programming relaxation at p equals 11. And there's been a recent numerical study of scaling of QAOA on random set problems, and it appears to scale better than state-of-the-art K-set solvers at k equals 8. Combined with amplification, this gives you slightly better than Grover, slightly better than quadratic speed up on random set, which is very promising. To give you a sense of how close we are to running this on hardware, some recent, you can think of sort of the size of the QAOA circuit you have executed as the product of number of qubits n on the y-axis, and the number of steps of optimization, number of these pairs of alternation operators p. Switch to laser. And that some of the recent hardware demonstrations are, one is from the Los Alamos group, where they show n equals 127 and p equals 1. And in some cases, they do n times p equals 254. So here by p, I mean how many layers do you do where adding extra layers still gives you better performance. Because of course you can have an arbitrary number of them, which is going to get maximum at mixed state in the end. And so they get only p equals 1 on hardware, on IBM reliably. And another example of a benchmark, which is a benchmark that we ran here at JPMC on Quantinuum's device, where we got n times p 200 reliably. So on n equals 20, p with 10 layers always gave us a better solution than 9 layers. And we had a hero run of 300, so p equals 15. And this was on previous generation Quantinuum hardware. So this gives you a rough sense of the scales at which we can execute this on hardware. The problem on which we're going to develop our theoretical results, and our numerical results are going to be slightly more broad than that. But the theoretical results are for the max cut problem, where the goal is to partition the set of vertices of a graph into two disjoint parts, such that we maximize the total weight of edges spanning the two parts. So on the right in this cartoon, we partition the set of nodes into blue and purple, and the edges that are cut are highlighted in red. The cut is the sum of the weights of these 4 edges. And I will call this problem unweighted max cut if all the weights are unit. It's a very well studied and a very hard problem, which famously inspired the development of a lot of the semi-definite programming techniques for computer optimization. This circuit, the QAOA circuit for this problem, looks as follows. Our initial state is uniform superposition over computational basis state. Our phase is, as before, the diagonal operator encoding the cost, and the mixer is simply time evolution with transverse field Hamiltonian, which is sum of power dx on each qubit. So that's our setting for the theoretical results. Now, the nice thing about MaxCut, and the reason that it's well studied, is that optimal QAOA parameters are available in many cases. So, for example, for large girth regular graphs, or for many random graph models such as Chong-Lu or Erdős-Rényi in the infinite size. And in the cases where analytical QAOA parameters are not available, they are easy to optimize. So, for example, this figure on the right shows the QAOA energy landscape, that is the expected quality of the solution of the QAOA as a function of the 2 parameters beta and gamma. And you see that as long as you roughly know where to start, so here in this region, it's nice and smooth, as the 1D slide shows, it's easy to find this optimum numerically by just going downhill. There's no bad local minima around it. The analytical result for parameters is what enabled statements like the one I quote here, which is that QAOA for max-cut on large girth irregular graph is competitive with conjecture-free classical algorithms p equals 11. It was, when this paper came out, this archive reference, it was beating all conjecture-free classical algorithms, but Mate Hastings came up with a better algorithm shortly after this appeared. So now it's not the best algorithm, but it's competitive with the best classical algorithms. Now, if we introduce weights into our problem, in our case, we introduced non-integer edge weights for the graph on which we're solving max-cut. The parameter optimization problem appears to become harder. And we will show later that this is not quite the case. But if you do naively and just directly plot the same quantity for this new problem, you will see that it is indeed a much nastier landscape. So looking at the one on the bottom, it's the same graph, but now with weights. And you see that now we're searching for this tiny peak around origin. And you can see that the landscape is very rugged. So even if we land here, very close to the optimum, but not quite the right place for our initial point, we will not recover the optimum because we will get stuck on one of those local minimas here. You can see you can get some intuition about why it behaves like this by examining the objective and closed form and noticing that you have all these sine and cosine terms in product. If all weights are unit, then they are roughly on the same length scale, so they come in and out of phase nicely and you get this smooth landscape. Whereas if they're all different non-integers, different floating point numbers, then they will be all out of sync, which will create these rugged, highly oscillatory landscape. And they will only come in phase when W times gamma is very small for all of them, so near origin. This also makes the landscape non-periodic. So in general, it's not clear where to cut off this box, which makes it, in principle, hard to optimize. Now, let me summarize our results. First, we derive globally optimal QA parameters for weighted max cut at p equals 1. Note the importance of global optimality because the landscape is in general not non-periodic. So numerically, it's very hard to tackle this problem of obtaining globally optimals anything on an unbounded domain. We do this by, en route to proving this, we prove rigorously that this first local optimum that I was showing you on the previous slide, near origin, is indeed the global optimum in certain cases. For when p, when the number of operations is greater than 1, we derive a correspondence between the QAOA energy landscape for weighted and unweighted max cut. This connection enables us to take the analytical results for unweighted max cut and apply them directly to weighted cases. For example, if we have parameters from unweighted max cut, now we can use them for weighted max cut. And we show numerically that it works quite well. And we prove concentration. So we show that the derived results hold with high probability for a random instance, where random means random over the choice of weights. Finally, we take these theoretical results for weight max cut, and we propose a heuristic rule that we demonstrate numerically far outside of its theoretical assumptions. So we take a look at the constraint portfolio optimization with a Hamming weight constraint, and we use Hamming weight preserving XY mixer and QAOA. And we still see that our simple heuristic improves parameter optimization drastically. Now, for the rest of my talk, I'm going to first walk you through the theoretical results to give you roughly a flavor of how they are achieved. And then I'm going to show you numerics confirming that this works well. That would be maybe a good time to pause if there are any questions from the audience. I don't know how you guys usually do it. Is it through chat or people just unmute their phones?
We will normally have a question on the session after the main content. So like mostly audience will ask questions by unmute themselves or tapping chat box after the main content.
Okay. Oh yeah, then I will just continue. Yeah, and then we can have a Q&A then. Okay. So our setting for the theoretical work, for the theoretical part of the results is as follows. We look at expected QA performance on large girth regular graphs with IID edge weights. So we make two assumptions: large girthness of the graph and IID weights. And the object we study is the expected QA performance with the expectation taken over the weights. Now for p equals 1, we can take that trig formula I was showing you on a couple of slides before and just use that, take the expectation of that. Now, we derive optimal parameters in the infinite size limit. The central trick that enables this is we need to define a quantity that has a limit. Because if you just take infinite size limit of this expectation, you're not going to get anything. And so for this, we define a weighted analog of cut fraction. So in an unweighted case, the cut fraction is the ratio between number of edges in your cut and the total number of edges. We define an analogous quantity where we now in denominator have the expected total edge weights, total weight of the edges in the graph. Then we take this cancels out the first term. So this is random guess, 1/2, plus some deviation from random guess. So this quantity describes our performance, how much better we're doing than random guess. And now we take the limit of this quantity, which gives us the infinite limit QA objective which would then obtain optimal parameter for by using sort of very elementary math. This term here is the contribution of one edge. We're going to have the same term for hierarchy, and the central observation is that we use this assumption on large girthness and IID edge weights to make it so the contribution of each edge is the same. It's not this how these assumptions enable our results. You can note that the same thing would work as long as contribution of each edge is the same. So perhaps so other graph models that have that are statistically uniform, that is, each edge is statistically like every other edge, the same techniques can probably be worked through, though the math may be a little bit more complicated. Doing this gives us the optimal parameters in the infinite size limit, which where dependence on the edge distribution now comes into gamma as 1 over the square root of the second one with the edge weights distribution. In addition, of p equals 1, we prove concentration. Specifically, we use simple observations on if you have, let's say, some assumption on distribution of your weights such that it's some Gaussian weights bounded, and the QA objective is Lipschitz, then from standard results on the concentration of Lipschitz functions of some Gaussian or bounded random variables, you get concentration results on the QA objective. This gives us, this implies that the results we obtain in expectation will hold the high probability for a random instance. Moving on to p greater than 1, so more than one pair of alternating operators, we can decompose our objective in the same way. So we have the random guess component, and then the component that is the sum of contribution of all edges. And these are all equal because for large girth regular graphs, from the point of view of each edge, all QAOA sees is a tree. Now, the graph is weighted, so each of these edges has a weight on it, but it works out to be so that if you take the expectation, all of these edges start looking the same as long as the edge weights are IID. And then for the contribution of each edge, we use the iteration from this paper of Joao Basso and Eddie Fari and the other folks from the Google group, which derives this contribution in the unweighted case. Now, in the expected case, it's not too difficult to adapt it to the weighted, to the case where we have edge weights on this tree that QAOA sees from each edge. And this iteration is what we use to derive the correspondence between the weighted and unweighted case. As I mentioned earlier, similar results can be worked out as long as all edges contribute equally. Okay. Again, we studied the infinite size limit. So again, we need a quantity that has a limit. We define the same weighted analog of cut fraction. It's exactly the same as for p equals 1. And then what we do is we derive a correspondence between this quantity, so how much better we're doing than random guess in the weighted case, and the analogous quantity for the unweighted cut fraction. Specifically, we show that the two are equal in the infinite size limit up to simpler scaling. And this gives us thus desired connection between the weighted and unweighted case. Specifically, if we have parameters that are optimal for the unweighted graph, this gives us optimal parameters for the weighted graph by following the simple rescaling. As a side note, an object with important connection to max cut problem is the Shannon-Kilpatrick model, which is all-to-all, which is a spin glass. You have all-to-all ZZ terms with couplings coming from the standard normal distribution. If we define QA energy on the SK model, it is known to be equal to this eta quantity defined for the cut fraction for the max cut problem. And of course, because we derive a connection between unweighted max cut and weighted max cut, you get a connection to the SK model for free. Now, the question that is natural to ask is, analogously to how we introduced weights to max cut, we go from unweighted max cut to weighted max cut, can we introduce some bias into the SK model? So instead of having standard normal weights, standard normal couplings in the SK model, what if we have some couplings that are, let's say, not at least normal with some mu and sigma, which are not 0, 1. Now, for the SK model in the infinite size limit, this quantity is just the Parisi constant. This is very famous results in statistical physics. Now, for the biased SK model, we observe that if the mean of the couplings does not scale with n, which is the sort of natural regime to consider. This is the regime we consider for the weighted graphs. Right? In weighted graphs, in the limit of infinite, in the limit of n goes to infinity, mu of our edge weight stays constant. We do not change the distribution with the scale. In this natural regime, we get trivial behavior. So our limiting behavior is just essentially mu, which is extremized by all spins being aligned, or all half of the spins being aligned and another half being aligned in the opposite direction, depending on the sign of the mu. So this is a trivial behavior. This is not a hard problem to satisfy this limiting behavior. Now, what we find is that if mu decays as 1 over root n, then we get some non-trivial behavior. So we get some contribution from something that looks like an unweighted problem. So you have the Parisi constant there, and then you have the second term in this limit. Now, perhaps this exists in the literature somewhere, but we couldn't find it, so we rederived it as sort of a natural thing to consider next. But one thing we have two questions about this. So one is, is there analysis out there for this biased SK model? And second, what can we learn about QAOA by analyzing it? Because if you think about this biased SK model, it is kind of like a general QAOA in a way. Like if you think about a general QAOA, let's say QAOA formulation of portfolio optimization, it has these all-to-all couplings, and they come from some distribution that's even nastier than this, right? So it's definitely not standard normal, and it's definitely not centered. But perhaps something can be glanced by studying the slight generalization of the SK model for QAOA. And this is more of an open question, and I would be curious to hear your thoughts. If you know something about such results, email us. Or maybe attach it to your internship application. Okay, let's see how well it works numerically. So we take a large data set of graphs, 34,000 graphs, which are far outside of our theoretical assumptions. So remember, theoretical results are in the infinite size limit and large girth regular graphs, and we'll look at small graphs that are general. So definitely have triangles in them, and so on. And we see that our parameters give us QAOA performance that is within a few percentage points of the optimal. So even far outside for a wide range of weight distributions. So even far outside of theoretical assumptions, we get good performance. Finally, the heuristic rule is the parameter setting rule we propose for max cut essentially boils down to rescaling your objective by the second moment of the edge weights. You can take this idea and apply it to any general binary objective. So let's say your objective is some f that is defined as a polynomial on spins with corresponding with coefficients w. You can rescale your objective by the second moment of the coefficients, and then, for example, optimize QA parameters as usual. We test this proposal on the portfolio optimization problem with budget constraints, where our goal is to maximize return, use a vector of expected returns, while minimizing the risk. So sigma is the covariance matrix. MQ is some coefficient controlling the trade-off between the return and risk that is desired. And we have a constraint on the budget, which we model as a cardinality constraint on the set of things we can include in our portfolio. So a Hamming weight constraint. To solve this problem, we use QAOA with the following circuit. Our initial state is universal position or all Hamming weight K states. And our mixer is time evolution with this XY model, which preserves Hamming weight. So all of our Q evolution happens in this Hamming weight K subspace. So every time we measure a bit string, it will always satisfy our constraint. And then we perform optimization within the subspace. Now, first, qualitatively, we can see what happens when we perform this rescaling, which we have outlined earlier. So heuristically rescale your objective by a sample estimate of the second moment of your couplings. We see that we go from this landscape on the left, which has, first of all, much larger variance with beta than with gamma, which makes optimization harder. And second, it's very flat. So if we replot the same landscape as this on the length scale of the rescale objective, we see that it's all, pretty much all yellow. So all corresponding to the bad regions of the rescaled landscape. In addition to now rescaled landscape having clear unit variance in all directions, making it much easier for our optimizer to converge. So qualitatively, this suggests that this rescaling should make the landscape much easier to optimize. And we indeed see this numerically. So we take and we run QAOA parameter optimization from the optimal parameters for the SK model for this problem. We always recover the same local optimum because we simply start from somewhere near origin and we go downhill. And it turns out that the optimizer will always find the same local optimum. So it's locally convex around origin. But what we're asking is how long does it take us to find this local optimum? And for the same optimizer, we use here Babaikwa, we see that we take on average 7 times fewer iterations to converge to the same local optimum, suggesting that the simple rescaling rule drastically improves our parameter optimization performance. To summarize, in many settings, QAOA parameter setting can be challenging, but we propose a simple heuristic rule that works well for a wide range of problems. This heuristic rule is inspired by rigorous analytical results for weighted max cut, for which we derive analytically optimal parameters in a range of settings, as well as concentration results for QAOA objective. You can see our paper for additional details and more numerics. And finally, remember to apply for summer 2024 internship program. The easiest way to hear more about it is to follow me on LinkedIn and follow, of course, our group lead, Marco Pistoia, on LinkedIn as well. Thank you very much for your attention. We have plenty of time for questions, I think.